everybody. Today I want to share with you a new topic, electrode potential. Myself, Dr. Digna Varghese. Origin of electrode potential. According to electron theory of metallic bond, a metal lattice is consists of metal ions bound together by a sea of electrons. Sea of valence electrons. Okay. Consider a metal which is in contact with a solution of its own that we can represent it as Mn plus. There is two mutually opposing processes possible. Okay, one is some of the metal ions may go into solution as Mn plus, leaving behind an equivalent number of electrons on the metal. In such case, the metal ions acquires a negative charge and the solution acquires a positive charge. Here you can see a system in which some of the metal ions go into solution as Mn plus, leaving behind an equivalent number of electrons on the metal. Okay, so the metal get a negative charge and the solution acquires a positive charge. In a second case, some of the metal ions from the solution may enter into the metal lattice, making the metal positive and solution negative. Here you can see metal is in contact with its own ions in solution. So here the sum of the metal ions from the solution to enter into the metal lattice. So the metal get a positive charge and the solution get a negative charge. So these are some actions or opposing processes possible in the system metal ion. Okay. Always one of these tendencies will predominate. But in any system, there is always this equilibrium exists. That is, metal in the solid state in equilibrium with metal in the solution plus electron. So, according to the electron C theory, the metal lattice consists of metal ions bound together by a sea of valence electrons. The charge developed on the metal attracts. Here, the charge developed on the metal attracts oppositely charged ions in solution. Okay, here the metal ion has the negative charge, so it will definitely attract what charge? A positive charge ions in solution. Okay, here the metal has a positive charge, so it will attract a negative charged ions in solution. There is an electrical double layer is formed at the metal solution interface. This is very important. An electrical double layer is formed at the metal solution interface. You can see here the metal ion has a negative charge and it will attract the oppositely charged ions in solution. That the negative charge of the metal ion attracts positive charge of the solution ions in the solution. So here a electrical double layer formed at the metal solution interface. In other case, here the metal atom has the positive charge and the solution is negative. So The positive charged metal ions will attract negative charged ions in solution. So here develops a electrical double layer at the metal solution interface. So there is an potential difference is set up between the metal solution interface. Here also a potential difference set up between the metal and the solution. The equilibrium potential difference is called the electrode potential, and it is obviously a measure of the tendency for oxidation or reduction to occur at the electrode. Okay, there is an equilibrium potential difference occurs. So these are known as electrode potential. Now we are going to define the single electrode potential. Single electrode potential is a measure of the tendency of an electrode to lose or gain electrons and is the equilibrium potential difference developed due to the separation of charges at the metal solution interface. When a metal is in contact with its own ions, the factors influencing the electrode potential is first one is the metal and its ions. Second one is the concentration of the metal ion in solution. Third one is the temperature. So the definition of the electrode potential is the tendency of an electrode to lose or gain electrons. Electrode to lose electrons means that is oxidation electron. Gain electrons means reduction electron. So single electrode potential is actually is a measurement of the tendency of an electrode to oxidize or reduce, and there is an equilibrium potential difference exists or developed due to the separation of the charges. If it is a metal as a positive charge, it will always attract a negative charge species or parts from the solution. So there is a charge separation occurs, and this charge separation at the metal solution interface, a potential is developed that is known as the electrode potential. Always metal. For example, copper is in contact with the copper sulfate solution or zinc is in contact with the zinc sulfate solution and so on. So this is the single electrode potential. Next one is the factors influencing the electrode potential, the metal and its ions. Okay. Second one, the concentration of the metal ion solution. What will be the nature of the metal ion? What will be the concentration of the metal ion solution? If it is a 1 molar, 2 molar, 0.5 molar, etc. What will be the temperature? So as the temperature increases, the potential also increases because the movement of ions always increases due to the increase in kinetic energy of the ions. So these are the factors which will affect or influencing the electrode potential. Mode of expressing electrode potential. We know electrode potential is a measure of the tendency for the metal to get oxidized or its ion to get reduced. For example, metal to get oxidized means metal ion undergo oxidation reaction to form metal ions and electrons. Oxidation is the removal of electrons. Metal ions to get reduced means metal ion accepts electrons to form a reduced form that is metal. So electrode potential is a measure of the tendency for the metal to get oxidized or the metal ion to get reduced. There are two types of electrode potentials, oxidation potential and the reduction potential. Oxidation potential is the measure of the tendency for the metal to get oxidized. Reduction potential is the measure of the tendency of the metal ions to get reduced. According to IUPAC, the latest sign convention adopted by the IUPAC, the electrode potential should refer to reduction potential. That means electrode potential means the term electrode potential means the reduction potential. Both according to IUPAC, both the oxidation potential and the reduction potential are numerically equal but of opposite sign. So negative sign for oxidation potential and the positive sign for the reduction potential. Negative sign for the oxidation potential and the positive sign for the reduction potential. So both the values are same but of opposite sign. You can use a code for remembering these signs, that is no problem. No means negative sign for oxidation potential and problem PR means positive sign for reduction potential. So you can use this code to remember the sign convention of electrode potential. Measurement of a single electrode potential. It is impossible to measure the absolute value of a single electrode potential because a half cell cannot function by itself. What is a half cell? Half cell means a metal ion with its own contact with its own ions in solution, that is zinc rod in zinc sulfate solution. Another half cell is copper rod in copper sulfate solution. These are half cells, but we cannot measure the absolute value of a single electrode potential because half cell cannot function by itself. So we can measure the difference in potential between the two electrodes, okay, by coupling them to give a galvanic cell. Here we cannot measure the electrode potential of a half cell, that is zinc in zinc sulfate solution or copper in a copper sulfate solution, but we can measure the difference in potentials between these two electrodes by coupling them to form a galvanic cell. Here you can see a galvanic cell diagram. So we can measure the electrode potential here by coupling these zinc electrode and copper electrode. So we can measure its single electrode potential. Okay. Measurement of single electrode potential. We know it is impossible to measure experimentally the absolute value of a single electrode potential because a half cell cannot function by itself. Hence, what is possible to determine the potential of an electrode related to a reference electrode whose potential is arbitrarily fixed. Here we are using a reference electrode as normal hydrogen electrode or standard hydrogen electrode. The normal hydrogen electrode, which is coupled with the electrode under consideration through a short bridge to form a complete galvanic cell like this. If we have to measure the zinc electrode potential, we couple the zinc in zinc sulfate solution, that is a half cell, with a reference electrode. Here it is a standard hydrogen electrode or a normal hydrogen electrode by a salt bridge, and we can measure the electrode potential of the zinc electrode. Okay. The difference in the potential between the two cells, here the zinc cell electrode and the hydrogen electrode, using a potentiometer. Here you can see the figure of potentiometer that are common in all MSc lab. And potential of standard hydrogen electrode is arbitrarily fixed as 0. Okay. So measured potential difference is numerically equal to the potential of the electrode under consideration. Here, if we are measuring the electrode potential, its standard hydrogen electrode potential is 0 and we get the potential of zinc electrode. So the half cell is connected to the one of the reference electrode. We are using here the normal hydrogen electrode or standard hydrogen electrode as the reference electrode. Here you can see the normal hydrogen electrode schematic representation. Here standard hydrogen electrode which consists of a platinum wire which is attached to a platinized platinum foil which is kept in dipped in the 1 molar concentrated hydrochloric acid solution. Pure hydrogen gas at 1 atmospheric pressure is constantly bubbled into the solution at 298 Kelvin. Okay, so this is the normal hydrogen electrode setup. And the electrode is represented as platinum, hydrogen, 1 atmospheric pressure, H plus, aqueous 1 molar. So NHE or SHE is represented, the cell is represented as like this. It has been arbitrarily assigned a potential value of 0 volt. All other electrode potentials are expressed relative to this value. Okay. And the electrode reaction for the standard hydrogen electrode or normal hydrogen electrode is 2H plus 2 electron in equilibrium with hydrogen gas. H plus accepts electrons to give hydrogen gas. This is a reduction step. Hydrogen undergo oxidation in the reverse direction. That is the backward reaction here. That is removal of electron to give H plus ions. H plus ions, that is oxidation. So standard hydrogen electrode reaction is this. So we can connect to any half cell and measuring the potential difference and for the SHE the value of the electrode potential is 0. So we can measure easily by connecting with this electrode and measuring the correct value for a single electrode or a half cell. Here we are going to discuss standard electrode potential. An electrode is called a standard electrode if its electrolyte concentration is 1 mole per liter. If any gas involved in the reaction whose partial pressure is 1 atmospheric pressure and the temperature is 298 Kelvin. These are at the standard conditions. The reduction potential of an electrode at standard conditions measured relative to the standard hydrogen electrode is called its standard electrode potential. The standard reduction potential of an electrode can be measured in this way for a zinc electrode. When standard zinc 2 plus electrode is coupled with the standard hydrogen electrodes in this way, you can see in this diagram, the electrode under standard conditions, that is here, which is coupled with the standard hydrogen electrode through a salt bridge that you can see in the picture. The potential difference between the two is measured using a potentiometer. This value is numerically equal to the standard potential of the electrode since the standard hydrogen electrode has been fixed as 0 potential. Okay. So if the reduction occurs at the electrode, if reduction occurs in this electrode, whose value in combination with the standard hydrogen electrode, the measured value is assigned as a positive value. If oxidation occurs in an electrode coupled with the standard hydrogen electrode, the measured value is assigned as a negative sign. For the zinc electrode is coupled with standard hydrogen electrode, the cell is formed as zinc 2 plus H2 platinum. We always representing left hand side as the oxidation electrode, that is anode, and right hand side as the reduction electrode, that is cathode. Okay, so zinc is a negative oxidation electrode, that is anode here, and the standard hydrogen electrode act as a cathode here. So the measured cell potential or EMF is 0.76 volt. Since the standard zinc 2 plus electrode act as a oxidation electrode here, so its value is negative 0.76 volt. That you remember our code, that is no problem, that is negative value for oxidation potential. Okay. In the same way as we can measure the standard electrode potential of copper electrode here, here you can see the standard hydrogen electrode and the copper electrode are connected by a short bridge, and the potential is measured by using a potentiometer here, and we can see the standard copper electrode is at the right hand side, so it is a cathode, and standard hydrogen electrode act as a anode here. So platinum hydrogen H plus, that is oxidation takes place in the standard hydrogen electrode, and copper electrode there is reduction takes place. Its standard electrode potential is measured by using a potentiometer. We will get a positive value, no problem. PR, positive sign for reduction potential. So this is the way we can measure the standard electrode potential of a single electron by coupling with a reference electrode like normal hydrogen electrode. Okay. So by this I conclude here. Thank you for your attention.